Please, next report, David Cheban, Moldova, please.
Thank you. The title of my talk is One-Dimensional Monotone Non-Autonomous Dynamical Systems and Strange Non-Chaotic Attractors. In my talk, I present some results concerning the special class of monotone non-autonomous dynamical system, namely one-dimensional monotone non-autonomous dynamical system. In framework of my talk, I present some results about structure of invariant set, global attractors, and minimal sets. After I give some application of this result to one-dimensional ordinary differential equations and one-dimensional non-autonomous differential equations. Here I present some standard notation in my talk. My talk consists of 3 parts. In first part, I will present 2 typical examples of differential, respectively, differential equation which generate one-dimensional monotone non-autonomous dynamical system. In second part, I present some general results concerning the general or abstract one-dimensional monotone non-autonomous dynamical systems. Excuse me, this is my neighbor which make reconstruction. Excuse me again. In the third part, I present some application of my result to differential and differential equations respectively. First part. In this part, I consider 2 examples. First example, which is scalar differential equations on R on real axis or semi-axis. Consider differential equation 1, scalar differential equation. Here, sigma ty, this is position of point y at moment t on the base dynamical system on the space y. In reality, equation 1, this is a family of equations depending on parameter y, small y from capital Y is this phase space of the base dynamical systems. Below, I suppose with the right-hand side f or equation 1 is regular. This means that the problem for equation y is uniquely there is a unique solution defined on semi-axis R plus. This solution continuously depends on initial data. It is well known from the general property of solution of differential equation y that function phi as function of 3 variables, time, initial data y, and parameter y, possess 3 properties. First property, this is initial condition. It means that function phi at initial moment t equal to 0 equal to y. Equal to u. Second property, which is a semi-group property. Set property is continuity of the mapping phi. It means that correct, the question problem is correct. For one-dimensional equation, we have an additional property which is a monotony of function phi with respect to variable u. Namely, if u1 is less or equal to u2, in this case, we have this relation for every t non-negative and parameter y from capital Y. This means that every equation y, every equation 1 generate an object which consists of 3 parts. First, here we have R, which is the first space of equation 1. R, which is a one-dimensional Euclidean space for the real axis. Phi, which is this solution or motion generated by equation 1, and dynamical system y t sigma sometimes is called a base of or driving system for non-autonomous equation 1. This object, this triplet, is called a function phi possesses property 1, 4. 1, 2, 3, 4. In this case, this object is called a cocycle, shortly phi, over autonomous dynamical system yt sigma. If phi possesses property phi, is called this cocycle is called monotone. If first space, in our case, R is one-dimensional, in this case we have a one-dimensional non-autonomous dynamical system or cocycle system. I'd like to stress that here time is continuous. This means that in our case, time is the number of all real non-negative numbers, R plus. Now consider a second example of scalar difference equation. We consider equation 2 analogical as preceding example, but here we consider the time is discrete. We consider t belong to number of anti-positive numbers, or t belong to is an arbitrary anti-number. Resonance has, in precedent example, denoted by phi t y u y, a unique solution of equation 2 passing through point u at the initial moment t equal to 0. As in precedent case, y here is a parameter belonging to first space capital U, ut sigma is a discrete dynamical system on the base space y. I'd like to stress that in the precedent case, for differential equation, which function of f was arbitrary, as here we suppose supplementary additionally that function f as function of u is monotone. In this case, from the general property of solution of difference, non-autonomous difference equation, we have the same four properties analogical as in the precedent case. Namely, we have initial condition for difference solutions of difference equation. We have the semi-group property, but here the time t is discrete. And the continuity of the function phi as function of three variables: time, initial condition u, and parameter y. Additional, we have the fourth property: if the function f, the right-hand side, is monotone as function of u, in this case, we have the monotony of function phi in respect to variable u. We said that in this case, difference equation as generate an object which possesses the same property. We have here an object for a triple of an object consisting of three elements. One, fast space R, real the set of all real numbers with fast space for equation 2. Phi is the solutions or motions generated by discrete equation, difference equation. A base space or driving system defined on the base space capital Y. Here t, time, is discrete, and motion sigma. This object is one-dimensional cocycle, which is a monotone with discrete time z plus zeta. This means that differential equation generate a continuous cocycle, one-dimensional monotone. The difference equation generate a one-dimensional monotone cocycle with discrete time. If, of course, it's his right-hand side f is additional monotone with respect to spatial variable u. And now we'll consider a special particular case of Pearson example. One, the base space y, capital Y, is a m-dimensional torus. In this case, this system or this equation is called quasi-periodic equation or quasi-periodically forced monotone map in literature. Denoted by tau m, capital tau m, the standard m-dimensional torus. On this torus, we consider a dynamical system, namely the irrational winding on tau m. In this case, we have a dynamical system, quasi-periodic, minimal dynamic system on the m-dimensional torus with spectrum of frequencies nu1, nu2, etc., nu-m. If these numbers are rationally independent. And now consider a particular case of Pearson equation, difference equation, namely equation 3, where function f is defined on the torus with respect to first variable, with respect to second variable is u belong to R, and take the real values. Repeating the same reasoning as in the precedent case, we obtain a monotone one-dimensional cocycle where on the base space we have a dynamical system on the m-dimensional torus, which is every motion is quasi-periodical, a dynamical system is minimal. minimal, which means that the trajectory is dense on the fast space. In our case, on the torus tau. This type of equations, of course, I suppose here that right-hand side f is monotone with respect to u, to spatial variable u. And the one dimension, once the torus is one-dimensional, this type of equations was intensively studied in the literature. There exist many publications dedicated to the study of this type of maps or equations. Namely, this series of publications was stimulated by studying the so-called strange non-chaotic attractors. Below, I will give more or less exact definition of this object, but in two words, is sufficiently complicated of point of view geometric attractors, but this attractor not chaotic. I will precise what's mean non-chaotic below. Now, second part of my talk. In second part, we said in the precedent part of my talk that we have two type of example, which scalar differential equations and ordinary and difference equation, one-dimensional ordinary difference equation with monotone right-hand side, which generate an abstract object. This object is called non-autonomous or co-cycle dynamical system with given driving system, autonomous driving system. This co-cycle is fast space is one-dimensional for this co-cycle. Additionally, the co-cycle generated by this type of equation is monotone. In the second part, we studied arbitrary or abstract non-autonomous dynamic system or co-cycle dynamic system, which possess the following property. One, fast space is one-dimensional. A second, this co-cycle is monotone with respect to fast space variable u. I give here the general definition what we mean with one co-cycle, but in reality I repeat more and more the same object. We have a triplet with fast space E here déjà arbitrary Banach space. In precedent case we had one-dimensional Euclidean space. Second object is a continuous map phi from product space. Here we have three objects: time t plus. Second is capital Y with the fast space of driving system, and E is the fast space of this abstract object. A mapping phi possesses the same three properties, not four. The fourth is the monotony. If we have 1, 2, 3, 1 is the initial condition, second semigroup property, third property is continuity of function. In this case, this object is called abstract non-autonomous co-cycle or non-autonomous dynamic system. If additionally this function phi is monotone, in this case, this co-cycle or non-autonomous dynamic system is called monotone or order-preserving dynamical system. After I formulate for this object some theorem where describe the structure of invariant sets of this object. Second, I formulate the theorem where I describe structure of global attractor of this type of dynamical systems. It said, unfortunately, I have not the time to formulate these results. Is a set result I formulate the theorem of this. We describe the structure of minimal sets. Minimal sets, a number of minimal sets of this type of dynamical systems. Finally, in the third part, I give some application of these results to scalar differential equations and difference equations. My time is finished. Thank you for your attention. Now, if you have some questions.
Yes, thank you.